Here's a recap of today's work on the wave equation solution, but I'm actually going to explain how I cooked up the solution, and then we'll do the intuition part at the end. Here's the wave equation as we've seen it in class. The velocity squared is 1 over square root of mu naught epsilon naught. Mu naught epsilon naught are the parameters of the permeability and the permittivity in a vacuum. And we saw that in fact the velocity, which is 1 over the square root of those quantities, is in fact the speed of light when we are working in a vacuum. Now to solve this equation, we do know the intuitive solution. So actually I'm going to write down the intuitive solution for this. We all know from previous work that the intuitive solution looks like some function g with z plus or minus vt, depending on whether you move modeling waves to the right or left. And let's see if we get that. So let's assume that the electric field is a given. It's propagating in z, and let's assume it's given by this relationship here, Ex equals f of z e to the j omega t. Now what we do is we substitute in to each of the derivatives. And this is a simple application of partial derivatives. We are not even doing products here, because when we differentiate with respect to z, t is a constant, and when we differentiate with respect to t, z is a constant. So let's do the differentiation. Two derivatives of this with respect to z is just second derivative of f with respect to z, still multiplied by e to the j omega t. Let's do the same on this side. Two derivatives of e with respect to t. We have f of z. This is an exponential. Every differentiation brings down the value that multiplies t. So we got j omega times j omega after two differentiations, j omega squared. Now what we do is we go back and substitute in the results of our differentiations into the equation here. So d squared f dz squared e to the j omega t, f of z minus omega squared over v squared e to the j omega t, and the e to the j omega t's cancel, and we have a simple second order ordinary differential equation for f of z. And there it is, and we know the solutions from circuits, that this is the sum of two exponentials with the variation j omega over vz and b times e to the minus j omega over vz. You could see that if you differentiate this twice with respect to z, you'll exactly satisfy that equation. Now what we'd like to do is interpret this solution further.